Hope all of you are fine. We are restarting our video lecture series after a short break. So today we are going to start with module 6, that is power system stability. So you may heard about the word stability in control system. So in this module 6, the topics covered in the syllabus are power system stability, that is steady state stability, dynamic stability and transient stability. Then the power angle curve and steady state stability limit. Then mechanics of angular motion, swing equation, solution of swing equation by point method, RK method, equilibrium criterion, its application, and methods of improving stability limits. These are the topics included in your syllabus. So, moving on to power system stability. So, you may heard about the word stability in your control system. So, what is stability? A system is said to be stable if it gives a controlled output even any disturbance occurs in the system. So such a system is said to be a stable system, that is, if it gives a controlled output even if a disturbance occurs in the system, then the system is said to be stable. So coming on to the power system stability, we have voltage stability in power system, rotor angle stability and frequency stability in power system. So you may be knowing that in a power system we have large number of alternators which are operating in parallel. That means they are operating in synchronism. So for the system to work properly, it is necessary that these generators or synchronous machines should maintain a perfect synchronism under all steady state conditions. That is, if any disturbance occurs in the system, even if any disturbance occurs in the system, these synchronous generators should continue to work in synchronism. So, when a disturbance occurs in the system, the power system should act properly within a very short time so that it maintains the synchronism even after the disturbance. So that is a stable power system. So in terms of power system, the stability means the ability of the power system to return to its normal or stable condition after being disturbed is called stability. The disturbances of the system that is occurring in power system is of various types. That is, examples are sudden changes of load, sudden short circuit between line and ground, line to line fault, all three lines fault, switching, etc. These are the normal disturbances occurring in the power system. So even such disturbance occur in the system should, all the generators in the system should work synchronously to maintain the system stability. So the stability of a system mainly depends on the behavior of the synchronous machine after the disturbance. So depending upon that, it is classified into three types. That is, the stability is classified into three types: steady state stability, transient stability and dynamic stability. So now we will look into what is steady state, what is transient and dynamic stability. In steady state stability, it refers to the ability of the system to regain its synchronism after slow and small disturbances which occurs due to gradual power changes. The small disturbance are normal load variations. That is, if small load variations occurs in a system and if the system regains its synchronism, then that stability is called steady state stability. So in steady state stability, the system is subjected to slow and small changes. It is very important. In steady state stability, the system is subjected to slow and small disturbance, and if the system regains its stability, then it is called steady state stability. Now, what is transient stability? In transient stability, the system is subjected to large disturbance. And if the system regains its stability even after a large disturbance, then the system is said to be transiently stable. That is, it is defined as the ability of the system to return to its normal condition after a large disturbance. Now, what are the large disturbances occurring in the power system? They are sudden removal of load, line switching operations, fault occurring in the system, and sudden outage of lines. These are examples for large disturbance occurring in the power system. The example for small disturbance are normal load variations in the power system. Now, the third one is dynamic stability. So, what is dynamic stability? Dynamic stability of a system denotes the artificial stability given to an inherently unstable system by automatically controlled means. That is, it is concerned to small disturbances lasting for about 10 to 30 seconds. That is, if the system is subjected to small disturbance and the system is regaining its stability using controlled means, that is the system will have some automatic control measures, that is automatic voltage regulator, governors, etc., and the system is regaining its stability using this control means, then the system is said to have dynamic stability. That is, the disturbance occurring in the system is small disturbance, but the system regain its stability by using control measures, then the system is said to have dynamic stability. So, hope it is clear what is steady state stability, what is transient stability, and what is dynamic stability. This is very important. The last year, there is a university question related to this area, what is steady state, transient, and dynamic stability. So, hope it is clear. Now, uh, mainly in this module, we will study what is steady state and transient stability limits, and how we can improve the transient and steady state stability of the power system. These topics are included in this module. So, stability limit. What is stability, steady state, or transient stability limit means? The stability limit in power system means the maximum power that can be transferred in the system without loss of synchronism. That is stability limit. We have to transfer maximum amount of power without losing synchronism. That is the stability limit. So to derive the stability limit, we must know the expression for power transfer in a power system. For that, we have to consider a synchronous machine connected to an infinite bus through a transmission line having reactance X1. The reactance of the transmission line is X1. This is synchronous machine equivalent circuit. This synchronous machine is connected to an infinite bus. So what is an infinite bus? An infinite bus has constant voltage and constant frequency even if there is a variation occurs in the system. Even if any disturbance occurs in the system, it will have constant voltage and constant frequency. Such a bus is called an infinite bus. So here a synchronous machine is connected to an infinite bus through a transmission line. The resistance and capacitance of the transmission line are neglected, so we are only considering the line reactance X1. So the equivalent circuit of the synchronous machine connected to an infinite bus through a transmission line reactance is represented as, this is the equivalent circuit of a synchronous machine. This represents the transmission line, and this is the infinite bus. Now we have to derive the expression for power transfer. Here, the V angle 0 is the voltage of the infinite bus. This is the voltage of the infinite bus, and E angle delta is the voltage behind the direct axis synchronous reactance of the machine. It is the voltage behind the direct axis synchronous reactance, that is induced EMF in the machine, that is E angle delta, and XD is the synchronous reactance of the machine. This is the synchronous reactance of the machine. This is the induced EMF, which is E angle delta, and X1 is the transmission line reactance, and V angle 0 is the voltage of the infinite bus. Now we have to derive the equation for power transfer. So we know that the complex power S equal to V into I conjugate. That is S equal to V into, what is I from the figure? It is clear that what is I, current flowing through the circuit, will be equal to E angle delta minus V angle 0 divided by JXD plus X1. Current I equal to E angle delta minus V angle 0 divided by JXD plus X1. So, complex power S equal to V into I. I is E angle delta minus V angle 0 divided by JXD plus X1 conjugate. Here we are taking XD plus XL as X. So S equal to V into E angle delta divided by this XD plus XL is taken as X. So X angle, this is JX. So J is angle 90. So X angle 90 minus V divided by X minus V divided by JX conjugate. That is equal to, if we take V inside, we get S equal to E into V by X angle delta minus 90, and we are taking the conjugate. So the angle becomes negative, so it becomes 90 minus delta. Here we have Jx in the denominator, that is X angle 90 in the denominator. If we take it to the numerator, it becomes angle minus 90, and if we take the conjugate, it becomes angle plus 90. So S will be equal to EV by X angle 90 minus delta minus V square by X angle 90. Now the active power transferred to the system. What is that? This is the complex power. So from this complex power, we have to write the active power and reactive power. Active power will be the real part of this equation, and reactive power will be the imaginary part. So to get the active part, we have to take the sine component, and to get the reactive part, we have to take the, to get the active component, we have to take the cos component and cos of the angle, and to get the reactive power, we have to take the sine component. So the active power will be equal to EV by X cos 90 minus delta minus V square by X cos 90. We know that cos 90 is 0. So this term becomes 0. So the active power will be equal to EV by X cos 90 minus delta. Cos 90 minus delta is sine delta. So active power will be equal to EV by X sine delta. So the active power is EV by X sine delta. Then what is reactive power? Reactive power will be equal to EV by X sine 90 minus delta minus V square by X sine 90. So that is equal to EV by X sine 90 minus delta is cos delta, and V square by X sine 90 is 1. So the reactive power will be EV by X cos delta minus V square by X. So this is the expression for active power transfer, and this is the expression for reactive power transfer. Now we know the equation for active power transferred is EV by X sine delta. This is the expression for active power transferred. So the active power transferred will be maximum when delta is equal to 90 degree. That is equal to, so the maximum power transferred will be equal to EV by X. So the maximum power transferred is EV by X, EV by X. That is the maximum power transferred. Now, if we draw this power versus load angle delta, then we will obtain a curve like this, because the active power transferred is EV by X sine delta. So it is a function of sine. So we will get a sine wave. This will be the curve for power transfer. So this is the graphical representation of PE and the load angle delta, and this curve is called the load angle curve. So this load angle curve is widely used in power system stability study. So this curve is called a load angle curve. It gives the variation of active power with respect to the load angle delta. So the maximum power is transferred when delta is equal to 90 degree, and as the value of load angle delta is above 90, then the power decreases and becomes 0. From this curve it is clear. If delta increases, P increases up to 90, then PE decreases and it becomes 0 at 180 degree. And if again delta increases, then the PE becomes negative. That is, the direction of power flow is reversed. That is, power is supplied from the infinite bus to the generator. Normally the power will be flowing from the generator to infinite bus. So if the load angle delta increases beyond 180 degree, then the power will be flowing from the infinite bus to the generator. And the power, active power, the total reactance between two voltage sources E and X is called the transfer reactance. The maximum power limit is inversely proportional to transfer reactance. So the next class we will discuss about the steady state stability limit and transient stability. Hope these topics are clear. That is power angle curve and different power system stability terms: steady state stability, transient stability, and dynamic stability. Okay, thank you.